Now please give an applause to Domagoj with his presentation about how one cool little Linux device was created.
Thank you. Hello, ladies and gentlemen. My name is Domagoj, and I'm working as a software engineer in the RIMAS technology. In the IVI department, mostly working on the development of our Linux OS distribution. Today, I would like to present you how we created one very cool small device that is used as the main control in some of our vehicles. So let's start. In this presentation, I will cover on what was the behind idea and the use case for the creation of this device. How does the hardware look like and how we made it. How we developed our software with Yocto and Qt. What were some of our problems we have encountered in the development. And lastly, I will cover a little bit of security and safety related topics. So, what was the main light we have followed? We as humans, we love the physical touch on every machine. We love to push every button we see. Even the red ones which say don't touch on it, we love to do it. With that idea in mind, we didn't want to have the main interaction with the vehicle and with the powertrain of the vehicle going through the touchscreen. We wanted to have something simple to use in a really fast moving vehicle, not to distract the driver too much. Yet it needed to be a beautiful detail in the interior. This is the final design of it. We call it the knob. It has the rotary switching function and also the push screen button and the graphics on the screen itself. We have created 3 variations of the same device. The only difference is the look, mechanics, and the graphics which are showing on the screen. On the far left, we can see the gear selector knob, which turns on and off the vehicle, and with the push on the screen, and also with the rotation, it controls the PRND, which park, reverse, neutral, and drive, to get the vehicle going. In the middle, we have the drive mode knob, which is changing the vehicle's behavior, going from standard to sport mode to cruise, eco, however the driver wants. And on the right, we have the torque distribution knob, which is actually used to customize the predefined drive modes and to control the limit of power going to each axle to customize it even further. What was the final hardware design we went to? Because it needed to be very small, we just added the 14 layers to accommodate everything on the small PCB. The SoC we have chosen is the NXP's IMX6 Ultralight, because it was powerful enough and it was small size and we had the experience with the platform from before. We are using the 8-bit parallel interface display, which is similar to those on very popular smartwatches, but we are just using the automotive version of it. The device needed to have Ethernet intercommunication with the other infotainment devices and the other knobs, and ability to transfer larger data than what we are used to in the normal cars, like the regular messages. And for the legacy interfaces and for the communication with the other ECUs in the car, we are using the CAN interface. Hardware is completely automotive grade, and it uses around 70 milliamperes of current on the standard voltage of the car. On the picture, you can see the final mechanical design and with the hardware placement where the PCB is located. You can see the cable going from the screen to the PCB itself. The screen itself is not rotating, and the rings on the outside do rotate. The additional PCB on the left is just the adapter board for the connectors for the wiring harness of the vehicle. It wasn't very practical in production to have the wiring harness connecting directly to the PCB itself, to the small one. The knob on the picture is the drive mode knob, which changes the behavior of the vehicle. And this, for example, is the PRND knob, which is actually the desk version of it for the development purposes. And yeah, we are using it quite extensively. This is the PCB itself. As you can see, it's very small, and I will send it upstream so you can take a personal look at it. For the software, we opted on the Yocto Linux, where we had the distribution made before for our other devices, and we wanted to accommodate just the new hardware in the schema, and we are using the Linux IMX kernel with it. Of course, we are using some of our custom device tree and some custom device drivers to work with our hardware that we made. The Qt, which we use for our application, does not support this SoC, so we needed to do a few tricks to get it working, but in the end, it works properly as any officially supported device by Qt. We have developed the GUI application within our team, and in the next slide I will show you one example on how it actually works. And we also have developed the OTA updates. We are doing the AB partition scheme on the OS, and we are using the OPKG package manager as a tool to install the application on the OS. Yeah, this is the example that I wanted to show you, how the application actually works and how the whole system works in general. The application is showing the change, the drive mode on the drive mode knob, and we are starting from the vehicle that is in the standard mode, and the user rotates the drive mode knob and changes the actual mode to sport. We are, from the application, we are reading the GPIO ports, and we are just checking if everything went okay with the transition. We immediately change the application UI to sport mode. In the meantime, we are sending the 0MQ packages through Ethernet to other IVI devices, to all user interfaces, and we immediately change the drive mode to have the immediate reaction to the user input. And in the meantime, we are also sending the CAN messages to the vehicle control units, which actually checks if that action can be done or not. And then if everything went okay, it changes the drive mode for the rest of the vehicle. For example, the rest of the vehicle means the rear spoiler going up, the whole car going down, or the car gets more power and such things. And also, you get the return CAN message as a confirmation that on the knob that it stays on the sport mode, everything went okay and everything went fine. So these dashed lines you can see on the picture, these are actually the confirmation paths. So we always have the return of the whole system that you can actually get the change properly. You can also see the available modes path with actually that is refreshing all of the time. Vehicle control unit sends the available modes to the knobs all the time, so we know where we actually can go and what can be done. So the user is always aware what he can do or he cannot do with the car. It is usually grayed out if let's say if you are not pressing the brake, you cannot go to drive from parking, and it is grayed out on the screen. When you press the brake, then you can actually go to drive, or if you are not, if your powertrain is not engaged. Yeah. Of course, in the development of every product, there are always some problems during the process. I will mostly focus on the software problems here. So the first one was mentioned a few slides ago, where we actually needed to manually enable the Qt working on our hardware to have the Qt application working. Yeah, it was problematic, but we managed to do it, and basically from the Qt we are on our own when we have some problems with the actual Qt. Another problem is regarding the Qt application is that at first we wanted to run too complex graphics, and the system being without the GPU, we just couldn't do it. It was very hard and it was very slow, and in the end we reduced the graphical processing to have everything running smoothly. You know, the designers always go over beyond, and then the developers need to do it, and you have problems. As we were using very specific display interface, we have added the support to have the 24-bit display working on the 8-bit parallel bus by packing the frames a little bit differently in the frame buffer. We are actually using 3 cycles of the change to actually get the picture on the screen. The next one especially triggers me. We wanted to have the Ethernet support in the bootloader, which meant porting the Linux device driver to U-boot. Sometimes it sounds easy, but the U-boot has the reduced number of system functions you can actually normally use on the kernel level, but not so much in the U-boot. So it actually meant the whole redevelopment and simplifying the driver to get it working in the U-boot. Other one is related to hardware being simple, where you want to save money by using smaller size storage and then having problems with the updates later on. We have went around this problem by using the main IVI as an NFS storage, where the update files are stored, and through the Ethernet network they are served to the knobs when they need an update. The last one mentioned here is the networking, where we have the limited number of devices in the network, and that it took some time to develop a proper way to configure each node in the network. We are using the static IPs and MAC addresses, and we also have the time syncing throughout the network, because all of the devices in the network need to have the proper time. As I said, I want to touch up a little bit on safety and security, not too much, I promise. The knobs, like how we managed to achieve the needed safety level. The knobs are controlling very powerful systems of the vehicle, and the users are there to do unexpected actions. The powertrain system and the vehicle control system, the vehicle control units, are there to protect the vehicle itself. So if user does something unexpected with the system will react accordingly and either stop the action or have the action in controlled manner. As I explained in the signal paths, there is always the available mode signals, which are reported from the vehicle side to the user, so the user is always aware what he can do or he cannot do with the car. The other one is regarding the Ethernet security of the knobs. The knobs have the firewall implemented, which limits what is actually transferred to them. Also, the knobs are not directly connected to the internet, and that path is controlled on the device that is connected to the internet itself. In the vehicle, the size and what exactly is connected inside the network is known to all devices, and in the network, which is very like, if you have all of the devices aware what the other devices are, you can do very good things with the security. Yeah, I have a few takeaways for the end. The first one is to never underestimate the processes. This one is regarding the processes of development, testing, integration, manufacturing, and also the process of creating a certain process. Don't underestimate any process of this. Like, each of them take time, take people, and take money. So never underestimate them. The second one is, in each of these processes you can have fun. Don't forget to enjoy it. And the last one is use Linux and use its potential. Thank you all. Q&A. So if you want to ask me something in person or just want to see the hardware, feel free to approach me at any time.
Sure. So what kind of silly things did the users do, actually?
I mean, most of this stuff is currently done by our testers, vehicle testers, like the proper drivers that know how to drive cars, and they like to change the modes like every 100 milliseconds just to see the reaction of the system. They are also changing the PRND while stationary, like this. And you get lots of silly stuff with the car, like the car starting to engage and then going back and forth. So you actually need the confirmation pass to be sure that you actually can do that with the car or not. I mean, the other silly things are regarding the drive, and these are not things that knobs do really control. So, yeah. Something else?
I have two questions. First of all, really interesting presentation. Thank you. You mentioned that you guys did a lot of work on, well, the bootloader and some other things on Linux level. Do you typically open source that for others to learn from you, or is it like completely proprietary thing?
Currently, we are not open sourcing that, but we are planning to. Like, we have really good plans to open source a lot of our stuff, what we do, because we are actually using some of that open source stuff, and we want to share it with the others. But the problem is always with our how do you call it, the army of lawyers within the company. So we need to fight them to actually get these things working, but we plan to do it in future, yes.
How's that battle going? Are you winning, or are they
Currently,
winning?
yes, but it will take some time to actually get everything set up, and
sense.
Yes, we are planning to do it.
A quick follow-up before the next question. Like, does it make any sense to contribute upstream any of the work that you've done to the Linux itself or to some subsystems of Linux or whatever, or is it like completely custom and then like doesn't?
I mean, we are contributing to Linux kernel. We do, like few of our colleagues have already done it. And I also wanted to do something in the following days because we have discovered some bugs in some drivers that we use, and that's basically it.
For people, so I come from, I think, a completely different realm than this. This is really interesting. This is why I enjoyed this so much. So for people like me who is like super far away from this, where do you even start with? Like, is there any like well-established books or sources on the internet? Like, if I want to make a device and work with Linux at that level?
I mean, we started directly from the Qt, where the Qt actually enables you to have embedded stuff, like for the Linux. Like, they're also offering some direct OSs. We started from that, doing it on the development boards from the NXPs, and Yeah, by using that. We started.
What about choosing the PCB? And is there like a website? This is all the PCB that exists. Choose whichever you like, or like I don't even know how to Google for that. I mean,
Yeah.
this is.
You have the officially QT supported devices, SoCs, and then you can buy for example, the development board. You can buy it off the shelf. You can deploy some Hello World examples of the QT, and then you can start developing your own application, and after that you develop your own hardware by using the same SoCs. And with the Yocto, you are able to do it very easily. Like, you can enable new hardware in the matter of days. Like, I started the company and they just gave me the device and said, there you go, this is the new device. Feel free to adapt our distribution to work on it. And in the matter of few weeks, I got it working. So it's not that hard. You learn through the process of Yocto.
I mean, if I would get a question someone come to me with what they told you, I would leave and never come back because it sounds so difficult to me. But
it's not. You get used to it.
Thank you.
Thank you. Come on, please.
Just a quick one. Are you developing that only for yourself, or the plan is to sell the device to other car manufacturers?
We develop this for our vehicles and also the vehicles that we sell, like to other manufacturers. But yes, we are planning to do these devices separately, like outside of the vehicle, and sell it directly to the customers.
Okay, thanks.
Yeah. That's it. Well, thank you guys.